do now is we will start looking at the software code and run through the software code. But before we get into that, I think you should also be aware of the advancements that have taken place in this area and how hot a topic this area of pedometer application is actually all about. Okay. Particularly this estimation of stride length. So we should spend some time at least here, understand basic equations that are associated with this stride length, and then look at the advancements in that area and then move on from there. Okay. Let me point you to some material, and essentially these are all textbook kind of material for your courses, and hopefully you will be able to download them, including the IEEE and other related publication papers that are associated, literature that is there. You should, if you read them, you will know where the state of art is. Okay. So that is the point. Let me point you to the first paper here, which is basically from analog devices. Okay. This is from an application note from analog devices. It says using the ADXL 202 in pedometer applications. So essentially it is a sort of a it is a accelerometer which is which they are trying to promote. Okay. But apart from that, it is useful to see what they actually have in mind. This paper actually gives you that idea of how much the accumulated error can actually be when you do double integration to get to distance, right. We said if you do double integration, one integration for estimation of the velocity and the other integration for the purpose of getting to distance. If you do that, how integration accumulation errors actually happen is all nicely described in this paper. So you can read it, you can download and read it. This basically I have marked some parts in different color with the help of our project staff Praveen, and essentially it is saying that inertial navigation systems use a combination of sensors and all that, and dead reckoning where the deviation of position from a known reference or a starting point is determined by integration of acceleration in each axis. And this is a very simple expression, right. This is nothing but half AT square which, and the initial position are which is essentially ut plus half AT squared is a very well known expression. So it is essentially doing this half AT square, and how at low speed the accuracy of such system over a reasonable length of time is actually very poor. Okay. So and then they take an example and show that there is indeed a, even if you consider the accelerometer and its temperature coefficient, which is essentially something like 2 fractional, actually it is nothing but 2 mg by for every degree Celsius, you will add something like no wait a minute. So it says the temperature coefficient of ADXL is approximately 2 mg per degree Celsius. A temperature deviation of even 0.5 degrees Celsius over 5 minutes would add 1 mg of error, more than the desired signal itself, right. So that is indeed the problem. And why is it more than this one? Because you can see that the desired signal indeed is 0.944, and here you get 1 mg. So that is indeed much more than the desired signal. In fact, a change in inclination of the accelerometer of just 0.06 degrees Celsius would be greater than 1 mg. So that indeed is causing the problem. So this paper is written by this person by name Harvey Weinberg, and essentially he comes up with a nice expression which we call the Weinberg expression for estimation of stride length. So you recall that I showed you a demonstration of the phone, and we said that if you take a phone which has three which essentially has this is the y axis. No, let us start carefully. This is x axis of the phone, this is y axis, and this is the z axis. This is nothing but the vertical displacement essentially. So this z acceleration is what we will try to use in all the related expressions, right. So when people walk, there is a z axis movement and of the body with each step. Now this is nice to say, but what is the actual thing that is happening, and how is it that there is a z movement or a vertical movement is interesting, and you can see that comes from this picture that you have here. This is a nice picture. What actually is happening is, this is the hip which is of the human, and you can see every time there is a right leg you move up, and you have the left leg which is placed back. There is a, you can assume that the leg is like a lever, okay, and such a lever essentially bends exactly at the knee point, and whenever you move this lever, flexible lever actually bends at the knee point, and that indeed gives a sort of a kick to the accelerometer. So essentially this is what the whole idea behind the z axis system, showing you a sort of a waveform which we discussed previously. You get a maximum acceleration and a minimum acceleration essentially happening because of movement of the leg and bending of the knee, and therefore the hip moves up and down and up and down, and you can see that all of this is well captured in this nice picture. So essentially the stride is nothing but the movement of this bounce which is shown here. So if you do, you can easily calculate the stride length by this very basic system, where bounce is the vertical displacement of the hip. The hip is moving up and down, which is the upper body, and this hip movement essentially is captured, and it goes on to come up with a empirical expression of how to calculate the distance. Weinberg in fact is the person who came up with this expression, which says distance is the fourth root of the average acceleration maximum, A max, that is the peak, minus the average acceleration of the minimum times n, which is for number of steps that you take, into k, which is some constant. And this is the trouble really, this k is hard to estimate, and this can differ from person to person, and therefore one may have to calibrate it for a specific person to ensure that the application that one builds is quite accurate for that particular person. So conclusion is that you could use dead reckoning to improve positional resolution of the system. It is not very useful for long term position measurement, although because of all these drifts and other related errors. Careful examination of the application can often reveal surprisingly simple solutions. It is your ingenuity on how you want to build applications, given the fact that you should not really end up with double integrals and integration, accumulation error, and so on and so forth. So let us look at one more paper, and let me give you some background of this paper. See, we are trying to do an IoT application, right, and we are looking at localization without GPS as a broad title, and we are trying to look at how to use these IMUs and all that. That is one approach. The other paper, this paper which we are going to discuss, actually says something even more and very specific, I would say. It says that why not use IMUs for detection of Parkinson's disease, some application on Parkinson's disease. So, you have to look at also that people are already looking at use of IMUs for very specific applications. So, let us turn our attention to this paper. It says comparative and adaptation of step detection and step length estimators to a lateral belt worn accelerometer. The title appears very general, but the very first line in the abstract says Parkinson's disease is a neuro degenerative disease that prominently alters patients motor performance and compromises the speed and so on. So, it is actually going into the details. The reason why this paper is important is because you look carefully, it says step detection method. Several algorithms are proposed in this paper, and we look at that paper. For example, there is one paper, so this is on step detection. You can see that sliding window summing technique is something that is proposed in this paper. Okay, there is a lot of references to previous work. At the same time, the authors also want to propose their own methods, right. And remember, this is very specific to the Parkinson's disease application. So, there can be you take the basic things and start adapting to very special requirements. Threshold based approach is one more method which seem to use. Then there is a sliding window averaging technique algorithm. Okay. Then gait speed and stride length estimations, a bunch of algorithms again there. You look at double pendulum model. The most common approach to measure average step length is to consider human gait as an inverted pendulum model. Based on biomechanical model, the authors propose a relationship between the step length and the vertical displacement of the calm of human body. Okay, so you can see that they talk about almost the same thing, leg length of individual from the pelvis near the COM region to hill, and H denotes the vertical displacement of calm. So, it is everything around the inverted pendulum, the hip pelvis region, that is exactly from where the vertical acceleration is being looked at. So, essentially we talk about the heel strike and the and then there is a stance, there is a heel strike and then there is a stance. Essentially two phases whenever we walk will essentially relate to heel strike and stance. Okay, then there is Weinberg's algorithm which is considered for stride length estimation as a function of difference in maximum and minimum vertical acceleration, the vertical displacement of the hip during one step. This method does not need any integration and thus avoids drift error. You can see the strength of Weinberg, which I also discussed in the previous paper, is because the fact that there is no integration error. And then you go on to find out for each step you have to do this, right. So, you have to do A max, average, no, you have to take the A max, then you have to take the A min, and then you have to keep doing it for every step. Some people adapt even averaging, moving averaging of A max and A min. Some of them seem to just take the absolute value of A max. So, many methods can be exist. You should keep trying. These are all variants that you yourself can try once you have the basic code with you, and very exciting results can be observed. K, as I mentioned, is a calibrating constant, and essentially it is a ratio of the mean stride length, real stride length that is there with that of the mean stride length that is estimated. Essentially it is just a ratio. So, then there are optimal parameters that this authors talk about for step length and other methods, and then they have some results associated with this particular application, which essentially should look at for the Parkinson's disease case. So, they have some results, they present these results, and essentially they talk about the 3 different methods for step detection and their associated performances, then strength and weakness assessments, sensor location, where should you put, and all that, and then there are also step length estimators, 3 selected step length estimators from literature they look up, then adaptation methods for each of the estimators. So in summary, this is an interesting paper also because it sort of gives you an overview of how active this area is. Okay, so I will take you to one more paper which is talking about step detection and adaptive step length estimation for pedestrian dead reckoning at various walking speeds using a smartphone, essentially what we have been talking of with respect to use of IMUs. This paper is also equally good, and as you can see they are looking at adaptive step length estimation. While this paper is interesting, they also have some nice ideas in this, and I found this to be a nice thing. Let us read the abstract and you will essentially get a very good idea. I mentioned to you in one of the previous slides about getting raw accelerometer data and then applying a filter, right. Now we could be applying, as I said, different orders of filters. Then you can have one of them which is quite popular is indeed the Butterworth filter. Here in this paper they do it differently. What they do is they do an FFT and then they do an inverse FFT back, and that is purely for the purposes of noise removal. So we will see that those results also. So you can also apply FFT and inverse FFT to smoothen the raw values that you get. So that is interesting. So okay, there is application of Lagrange multiplier and all that, so we can have a look at that. So let us read the abstract. This adaptive stride length estimator for various walking speeds. So you can see we apply FFT, fast Fourier transform smoothing for the data that you collect. Then we analyze this data set for step detection rules in order to detect walking steps, and then there is an adaptive estimator which is based on the model of average step speed. We accurately obtain the walking step length. To evaluate the accuracy of the proposed method, we examine the distance estimation for 4 different distances and 3 speed levels. As usual, claim is that the experimental results show the proposed method significantly outperforms conventional estimation methods. So what is the key takeaway from this paper? This point, adaptive estimator is what they use, which is based on the model of average step speed. Okay, so they have to use the average step speed in order to accurately obtain the walking step length. This is the big takeaway from the paper. But before we go to that, nicely written paper, particularly you examine this second paragraph here. 2 main algorithms for distance estimation. The first one is successive double integral based step length measurement of acceleration. We have discussed this enough now, you know that double integral based is not so good. The major drawback is error accumulated over the duration, and how does one correct it? There is a method. You do 0 velocity updates ZUPT, and by doing ZUPT you could essentially get rid of this to minimize, I would say, not get rid of, you will be able to minimize the accumulated error. Now the second type where researchers are looking at is do not do double integration at all. You have a verifiable relationship between vertical acceleration, which is nothing but yaw, which is nothing but z, which is nothing but what I showed you in this phone moving up and down. This is yaw, this is nothing but vertical acceleration, this is nothing but z axis, all are the same, right. So keep that in mind, and as we read we will understand them further. Vertical relaxation and the step length to estimate the distance travelled by a moving subject. So this is then you have empirical solutions for step length estimation using mobile. So many people have worked on it, and they describe all the nice work that has gone behind. So considering many things, many problems that are there, so this step length estimation method based on previously developed method, particularly Weinberg now you should have by hearted, which is quite straightforward. What will you do? 4th root of open bracket a max minus A min, you close the bracket, right, into n, that is for the number of steps that you take, into k, right, that is as simple as that, and k is something that you have to sort of tune it for every individual, and then you have a very good estimation of the stride length. So we will now define a so then they talk about the step length there. So to this end we let me just quickly say, considering these facts we propose a step length estimation method based on previously developed method to improve the estimation accuracy under the 3 speed levels of low, normal or high and high. Essentially it is also using the Weinberg expression and improving up on the Weinberg expression. To this end we define a unit conversion as a function of step velocity and determine the step length using Weinberg formula, and you can see that they do FFT operation to smooth the obtained accelerations before identifying the step phase using our step detection rules. Then they transform the sensor coordinate system to the world coordinate system for step length estimation, right, and after the step length process we estimate the step velocity. They use a linear regression model and thus determine the length of the step. Conclusively we sum all step lengths during travelling to obtain the walking distance. So in summary, even before you want to completely read this paper, this is what this paper captures, okay. So all the related works are mentioned here. You can see that the proposed Weinberg formula is this, and walking distance estimation is what they are trying to get to, and then they have an experimental setup which they talk about. You can see that z is nothing but yaw, it is moving up and down, and what they do is in order to do this experiment they actually tie the accelerometer to the leg, and this is very important because they really want to get to proper ground truthing, okay. And this paragraph is really very good. If you follow this you will understand something very nicely written here. For instance, if you take young guys, what is their speed at which they walk? 14 to 64 walk about 1.25 meters per second. Okay, older people, older pedestrians 65 and above go roughly 0.97 meters, roughly 1 meter per second, okay. And therefore there is according to some other observations, mean comfortable speed is about 1.27 meters per second for women and 1.46 meters per second for men, and whereas the mean maximum speed is 1.75 meters per second for women and 2.53 meters per second for men. You plot all this and then you look at other studies that have been done and you start plotting, you will get this nice average human walking speed which is on the x axis, a nice histogram that you can actually plot, okay. And then you will see that you can set the v bar, which is nothing but the average velocity, to about 1.36 meters per second with a sigma which is the is nothing but the deviation of human walking speed is about 0.29, right. So you can see this, and then they start using this basic data for all their further characterizations. So what a nice way to do it. So I would say it is a really well written paper. Then they do FFT for data smoothing. You can go through this in detail, but what is interesting is this. Look at the top picture which is the raw signal, and look at the smoothened signal. After you do FFT then you go back and do a the inverse FFT, and then you use the Lagrange multiplier y which was obtained from some other expression, and then you plot it back, you get back this nice smoothened signal of the z axis, which is nothing but the y which is nothing but the vertical displacement, which is nothing but the yaw essentially of the phone. Then there is a nice pseudo code which is talking about how you do the smoothing of the signals, and then step detection rules. You have to do some RMS concept for processing raw acceleration data, you use this expression, and then you go on, and then they try to improve this, improve on it. This is perhaps one paper which actually talks very well, and this picture, if you see, this picture is exactly what we were able to plot also. You will see that there is a heel strike, then there is stance, heel strike, stance, heel strike and stance, and so on. That is, this hip is moving up down up down up down, which is what we saw in terms of that hip movement was also called the bounce in the other paper, which is nicely matching everything. X axis is time and y axis is acceleration given in meter per second square. The results that you see are essentially that whenever there is a heel strike, you will see that it is the minimum, right, and whenever you go to stance, it goes to the maximum. Why? Because your leg, which is like a lever, sort of becomes straight and then moves the hip up. Moment that happens, you get a stance. So these peaks are essentially stance, and the heel strikes essentially are essentially the minimum point. So essentially it is just that part which is used, and then you have a nice algorithm, vertical acceleration based on walking distance and all. So this paper goes on talking about their own method of trying to come up with how to estimate the stride length. So the adaptive stride length method, what they do is, you have seen that value k in that expression, Weinberg expression. So instead of using that constant k for all steps, we derived, so they derive a k factor as a polynomial function of the average step velocity, and that is what this whole paper is all about. And so essentially you have to look for a polynomial function of the average step velocity, and then they do that, and then they obtain some, so they collect lot of data, they use some part of it for training and some part of it for testing data, and then they have their experimental results, which, and then they describe their experimental results, and finally they do show that there is some sort of improvement with the adaptive. They have a way to go with an adaptive k using this walking distance estimation method, and in particular they introduce this new step detection algorithm and step length estimator, and they have some results out there. You can go through this paper in detail and understand them, and perhaps arrive at something which you may want to try yourself.